Alright, so in order to progress in this section, where we're going to develop some of the more formal ideas of a Riemann sum and how we actually will calculate one, it's extremely useful and essential for us to understand this summation notation. So a summation is something just like this. It is essentially a way of saying, let's sum up, that's what this is saying, the sigma, the capital sigma, let's sum up terms that all look like this. We'll start off with an index value of m, so this is some number. It's an integer, it's a whole number. And we're going to start with that integer, so maybe we have like I equals 2. And then we would work our way, we'd plug 2 in, we'd get a term. So in this case, if we're starting with m, we have the m term plus, well, we would go in integer steps. So we'd start with m, we go to m plus 1, m plus 2, and we'd work in an orderly fashion until we get to n where we stop. And that's exactly what this sum is doing. For each integer from m to n, we plug it into this expression. So really this a sub I, we could have written it as like a of I. Oops. We could have written this as a of I. It really is a function of I. It's the function of that integer I. And then it produces an output. So this would be like the a of m output, and then we'd add it to the a of m plus 1 output, and we continue that until we get to our stopping value. So if we go ahead and write some of these things in, this is, maybe we'll call this the general term. It's a function of I. I is called the index of the sum. This m here is the initial index value. So I'll just say, in other words, it's our starting value. And here, this is the terminal value. It's where we end our sum. Let's take a look at these examples here. Evaluate the following sums. So here, we're going to have, so here our function is just a of I equals I. So in other words, we're supposed to just plug in these values here. So here, if we plug in I equals 1 into I, what do we get? We just get itself, 1. Then we increment, so here, this is the I equals 1 term, plus we're going to add to that the I equals 2 term, so 2, plus 3, plus 4, plus 5. Because this was our terminal, this is our stopping point, we will take I from the initial value all the way to the final value, plug it into the expression, and then add it to the next value of I. And here, this will always increase by whole number values. So if we start at 1, the next value is 2. There's nothing in between. Now that's not to say that when you plug this in, that this has to be a whole number. It may or may not. You know, we could have something like the sum from I equals 1 to 5 of I over 2, in which case this would be 1/2, plus 2/2, plus 3/2, so on and so forth. So these values will always be whole numbers, but whatever you get once you plug it into this expression, that can be anything. Yeah, it can be practically anything. So for part B, if you look at these two things, the only difference between this sum in A and this sum in B is that our variable is different. But I here, K there, K there. So this is exactly going to be the same sum. This is still going to be 1 plus 2 plus 3 plus 4 plus 5, which should be 15. So the actual name of your variable, of your index, doesn't matter. All right. Part C. Here our expression's a little bit different. Now our function is the squaring function. So this would be 1 squared plus 2 squared plus 3 squared, and that's where we would stop. So this becomes 1 plus 4 plus 9, which is 14. So in this expression here, generally speaking, I would put parentheses or something here to at least know that this whole expression is the general expression of the sum. There can be ambiguities where maybe you're only summing this, and then after the end of the sum, you'll then subtract 1. So just be careful if you're writing these down. In this, I think especially in the beginning of teaching this, I would like to have put parentheses here. So with that, we'll go ahead. Notice here that in this expression, we have a j, but our index, the variable of the summation, is k. So we should exactly do the following. We should plug in k equals 3 and get something. Well, there is no k to plug into, so we just get j minus 1. And then we should plug in k equals 4, but there is no k, so we just get the same thing. Plus, again, we should be plugging in k equals 5, but there is no k, so we again just get another copy of j minus 1. So altogether, we have 3 copies of j minus 1. And that's the sum. All right, here, this says we start at 0 and stop at 0. So we would just plug in 0 in for I, and that is both the final, or excuse me, is both the initial and the final term, so we just get 0. For f, we'll get sine of 0 over 4, so 0, plus sine of pi over 4, plus sine of 2 pi over 4, which is, I believe, just pi over 2, plus sine of 3 pi over 4, and then lastly sine of 4 pi over 4, which is just sine of pi. Which, of course, sine of 0 is 0, sine of pi is 0, sine of pi over 2 is 1, sine of pi over 4 is root 2 over 2, sine of 3 pi over 4 is also root 2 over 2. So we should get 1 plus root 2 as the answer. All right, in this next example, we'll take a look at some of these more intricate ways of calculating sums.